Hello, good evening everyone. Okay, I'm audible, right?
Yes.
Fine. So I think today's session is week five, solve with us plus week six, right? And I think we'll be having one more session on Sunday. That is on week six. Probably the timing is 6 to 8, but we will maybe we'll change that timing to 8 to 10. We'll see that, but that will not be only solved with us. I will cover some part of week six today, and the later part, right, that I will be covering it on Sunday. So how many of you have watched lectures for week 5 and 6 both?
Week 5.
Week 5 and 6 both have you watched both lectures?
Week 6 not completely watched.
Okay, week 5 is complete.
Only week 5 completed.
Okay, fine. Okay. So, okay, so we'll start week six today a little bit, right? Like I'll give you the introduction and everything about it. It's a continuation of what we have learned in week five, which is linear regression, and what are the different variations of linear regressions that are there in week six, which is ridge regression and lasso regression. How they are different from the linear regression which we study regularly. That is there. Uh,
So we will not have a solve with us session for week 5.
yeah. Today, so the first session, the first half of it, right? It will be solve with us for week five.
Okay,
Maybe
okay.
1.5 hours we'll be discussing week five. After that, later half an hour or 45 minutes, I will be covering week six. Will that be okay?
Yes, sir.
Okay. I think the deadline for week five is today, right? Week five grade assignment is today, and
Yes.
Yes, sir. Yes, sir.
yeah. So keeping that in mind, we will be having week five first, and then we'll start with week six. Okay. Yeah. So I'm sharing my screen in here. You guys can answer in the chat box in the Gmeet. Fine. So maybe we'll not. I'll not allow like much of the time, but yeah, I'll comfortable. Maybe I'll give you some minutes there so that we'll have to finish it by. Uh, okay, what's no extension, no extension there in the grade assignment deadline. Okay, so let's start directly with question number one of week five. You guys can write your answers in the chat box here. So this is your first question. I hope all of you are able to see the screen. The question is: suppose you are given three training instances x1 y1, x2 y2, and x3 y3 as follows. So x1 y1 is this is your. So what is the dimension of each xi here?
So
Two
2.
dimension. Yeah, and you have y which is a real number, right? Fine. Your goal is to predict the output y based on the feature where y hat is x transpose w hat, and w hat is it's a two-dimensional vector again, w1 and w2. Find the w hat that minimizes the squared error loss, right? Where y is, I think it is already given in the above data set, which is 110. It is given to you. uh, okay, and then if you guys don't know how to find out the inverse of any matrix, this is the formula for finding out the inverse of the matrix. So you need to find out w hat, which minimizes the squared error loss. So have like maybe 3 to 4 minutes to solve this, because it involves the calculations. I am giving you that much of time, and accordingly you'll have to write the answer in the chat box. Okay. So shall we proceed to the solution? I think 3 or 4 students have replied here. If you need more time, just let me know. Otherwise, we can proceed to the solution. If anyone is trying still, or it's done, shall we?
Sir, how many questions are there?
I don't know. Maybe we'll try to solve like 5 to 6 questions at least. Okay. So I think, yeah, I think 5, 6 students have said like the answer is given. Let us see, but this is the easier one, because you know, if this is a linear regression case, right? When we wanted to solve or we wanted to minimize the squared error loss, that loss will be given by what? I think the expression, right? Or the loss which minimizes this w, that w hat will be given as
X transpose inverse XY.
generally, but let's say if the inverse exists, then it is inverse xy, right? That is the loss which is there. I think in a simplified terms also you can just directly find it out by using this also. Maybe if this is xx transpose inverse and xy, if I just apply inverse term inside, what I'll get? Can tell me what should I get in here?
X transpose inverse into X inverse.
So transpose inverse to x inverse to xy, right? And that term can be identity matrix. So basically, if you just solve this also, that should give you the same answer. But that is the case when inverse exists, right? So fine, okay. Anyway, in lectures, I think we are preferring uh, this w hat, which is xx transpose inverse x and xy. So what is the dimension of x in this case? D cross n,
2 by 3.
right? So in our case, it is 2 dimensions
2 by
and
3.
number of examples are 3, right? So x1, x2, and x3, that is n equal to 3, and each of x is 2 dimensional. So you will have to find out first xx transpose, then you will have to find out its inverse, and then multiply that with this matrix xy, right? And if you do this calculation, so I think xx transpose is 2112, correct, after the calculations, and then xx transpose inverse will be this one, and if I just do the multiplication, I'll get 1 by 3 1 1, that is basically 1 by 3 1 by 3, right? So those who have answered right, for all of them it is correct. Maybe it is 0.33 0.33 or 1 by 3 1 by 3. Those who have answered it correctly, this is the correct answer. I hope you understand the procedure how to solve this problem. You need to first see what are the dimensions of x, and then use xx transpose to find out, like first then find out xx transpose. It will be d cross d, that is 2 cross 2 in this case. Then you will have to find out its inverse, and then just use this equation, right? It is called as a normal equation. Use this normal equation to find out the w hat. This w hat, these are the weights, right? Or this is the weight vector which gives you the least squared error loss, right? Okay, proceeding. If any doubts are not there, maybe I'm proceeding next, right?
So
Yeah, tell me.
why how we find like inverse of a matrix are taken the formula of that divided by the that is
So in this,
determinant.
yeah, determinant. So if this is my matrix, right, A, B, C, D, you'll have to find out its determinant first, then divide it by this, and then use the cofactor matrix. Right. So this is, I think, this is the cofactor matrix. I hope all of you know what is cofactor matrix is. And then I think
So we know
So
how to
after
calculate it, but like geometrically, I'm not sure. I know how to calculate it, but
no
geometrically,
calculation is required right here. It's fine. Like geometrical interpretation is not required in this case, I guess. How to?
Sir, after XX transpose,
Hmm.
so we have to do XX transpose inverse,
Hmm.
है ना? फिर उसके बाद क्या करना है?
Use this equation, no? What is this equation W hat? W hat is XX transpose inverse XY. So you already have calculated XX transpose inverse in the first step. Then multiply with this X matrix and then y. This X matrix, this part is XX transpose inverse. It's just multiplication, matrix multiplication. So this is matrix, this is vector, y vector. Just you know how
Okay,
to do
sir.
multiplications, right? It is simple.
Yes, sir. I know. Now, one more I want to ask: why we call W hat? What is in one word? What is W hat?
What is it?
In one word, what is W hat?
W hat is W hat is the weight vector, okay, which minimizes the loss. So generally, we know what is the equation of linear regression. It is y equal to W transpose X, right, plus B generally, right? Any simple linear regression equation, or it's like fitting the line to the data set, right? So if it is W transpose X plus B, right? But we are not considering biases in this course. So we are saying that all the data set is centered, or basically the weight vector is going through the uh, origin, right? So in that case, this is the equation. What does this gives to me, right? W transpose X. This is a equation of a line. Do you agree that?
Yes, sir. I understood.
Huh.
Yes, I understood that
And
part.
W hat is so since we do not know exactly what W hat satisfies this equation, we are actually finding this W hat, which is the approximate solution, right? Is the approximate solution because let us say if my all data points are lying on the same line, in this case, let's say this is the line, right? And if W hat passes through all these data points, correct? Let's say if it is W, if it passes through all these data points, there will be no error, right? The error will be like
Yes, sir. I understood, sir.
so
I
what
got
do
the
you
point.
understand?
Yes, I got that W hat type.
It's an approximate solution which minimizes the error. Since all this W cannot go through all the data points, there will be some error. That means what we are doing is we are saying we are taking the projections, and this is the approximate solution to the like the line which is passing through the all data points. I think we have seen that also in MLF. If you have studied MLF previously, that is what list error. I think list square solution, right?
Yes, sir. I just remembered.
हाँ,
Yeah, मुझे
that is
बाद
list
में
square.
याद आया.
Correct. Okay, fine. This is the second question for the data set given below. Uh, okay, it's already in D cross N. Y is the vector given to me as initialize W naught with 0, 0 with the initial vector with learning rate eta which is 0.01. Let WGD be the updated weight after one iteration of gradient descent, and WSGD is the updated weight after one full iteration of stochastic gradient descent by taking first two and the next two data points for the sample. So what batch we are using it here for stochastic gradient descent? What is the size of the batch? So batch size here is 2, right? Equal to 2, correct? So one is gradient descent, which will be using entire data set, which is X, which is 2 cross 4. Stochastic gradient descent, here we are using 2 size of 2. So you need to first find out the gradient for the first two example, and then the next two example, or no, next two samples, you can say, or examples, and we need to find out what is the difference between stochastic gradient descent weights and the gradient descent weight. So how will you calculate the stochastic gradient weight?
So we'll take the average.
Average, and you'll find it out, right? So yeah, so first compute W for these two samples, then the next two samples, take an average of it. I think you'll get some WSGD, and you just need to find out. So this is what the L2 norm, right? So you'll get two vectors, which is WGD and another WSGD. You need to find out its L2 norm of these two vectors.
Sir,
Hmm. Yes. Yes, you were saying something.
no, sir, no, it's okay. I was thinking something.
Okay.
Sir, for W1 and W2, we will have to consider all the points, right?
Wait, W1 means W1. What are you?
Right. First.
So okay, the WGD, right? This GD.
Yes.
You will have to consider entire data set. And for second is because one full iteration means generally it is in deep learning, it is called as first epoch, where you just go through all the data points. So here, since we are using the batch of two, so we'll
Okay.
calculate for uh, first batch, and you update the vector, and then you calculate for the next batch, you update the vector, and once you complete this four, right, that means entire data set, that is your one full iteration.
But in this one, we'll have to do two iterations, right? W1 and W2, right? First, we'll have to find that.
In which case, SJD case or GD case?
GD case.
GD case,
Okay,
no,
one only.
one only, right? Because we are using entire data set, so it's only one case.
WSCT.
So whatever derivative you're getting, right, you just use it. Actually, uh, it should be the same equation which you have already found it for, I think, the previous case, that X is transpose inverse. It will be like very closer to that answer, PD1.
Sir, can you go to the previous slide?
What are you saying?
Like, can you show the formula for inverse?
No, that formula I think it will not work, right? This one it will not work here.
Okay, okay, I was doing some mistake.
This gradient descent, right? Gradient descent is what? WT plus.
Yeah, sir, I got it.
Yeah.
I got what.
So for stochastic gradient descent, we have to take the average for all the data points, or
No. What you will have to do is, so as you do gradient descent, right? The
Mhm.
simple gradient descent. What you do there, you just plug in the entire data set where
Yes,
whatever the I think the derivative is there, right? Once you find
yes,
out the derivative with respect to W, you will
yes,
get some, and then you will put all the values of X, right, in there.
yes, yes,
Here, in that case, instead of putting all n values, you will put only few values, right? So in this case, we have only two values because its batch is two of size two, right? So you will put only two, then you will calculate the
So
W1.
batch size is 4, right?
No, it is the entire data set, right? Here in this case.
Yes, yes,
So when you do stochastic gradient, that means you don't use entire data set, you use some
yes,
part of it. So
yes.
here in this case, the some part is only two samples. In general, like whenever we do practical things, right, it will be like the data will be very huge. Correct? But here, since we are doing it mathematically, or like or we are trying to solve it analytically, right? In this case, the data size is two.
Sir,
Ah,
Sir, can you show the question?
yeah,
sir, basically in stochastic gradient also we will be
same equation.
finding the two.
So,
Okay,
okay,
the
I'll tell you
first
the same
one.
thing. I think, see, our gradient descent is what Wt plus 1 equal to
Yes,
Wt
W1, WT plus minus eta into.
del W
Correct,
T, or
correct. Del
basically
of
we
W, yeah.
del Wt, we say, let's say, if L is the loss, del L and at Wt, right?
WT, correct.
So initially you have 0, 0. So your loss will be
Right.
what?
Understood, sir.
Y minus Y hat. Uh,
Correct.
and I think you should plug in the values of Y hat. I think what is it, like minus W transpose X. Is that correct? This one. And you just try to differentiate this with respect to
Right, right.
W, right?
Correct, correct.
But when you differentiate, I think you will get some equation and that will have this X as a quantity, right?
Correct, correct.
When it is a gradient descent, you will use entire X, which is of D cross N. Fine. Suppose in this case we have 2 cross 4. You It's in gradient descent you use entire X, but in stochastic gradient the equation will be the same. The only difference here is at one iteration, let's say t equal to 1, right? It will have two uh, parts, right? Maybe I'll just say that it is t plus 1, or maybe let's say it will start from t0, t plus 1, let's say I'll call it as t w1. Okay, that is the first part of it. Here in this equation, the same equation you will be using, but X, whichever you are using here, it will have this dimension 2 cross 2, because,
Understood, sir. Understood.
right? And in the second thing, it is due to, again, this is the same iteration, only the second batch, and you use the next 2 by 2, the same equation.
Sir, that is what I'm asking, sir. In this one also,
Hmm.
the initialization, the W not initialized will be 0, 0, right?
Yeah, for this case.
For this case, yes.
Yeah,
For the next case, it will change basically.
you can use the previous one, right, which is already up.
Yes, and then we will have to average it, right?
Yeah, so see, in that case I think you, uh, it will be like this, no? Suppose you take,
1 by T, right? 1 by T something.
yeah, and then you will have to take like this, and I think, but in this case you don't, I think, need to average it out. I guess,
Okay, okay.
because you are
Yeah.
started from here, right? You end up in here, and then again you're taking the direction in another.
Then the final one we will have to take.
Directly it will be the answer, right? The other case is,
WSGD2 basically.
yeah, if you use W00 and you use the 2, right? Then you will have to add it and then average it out, I guess. We'll see that one. The average
Okay.
thing I'll
Okay, very good.
sell.
Fine, sir. We'll try, sir. Try
Yeah.
and
I hope it is clear right now. We'll see whether to average or not. We'll see when we see the solution. Okay. Just take two more. We'll discuss the solution.
so can you show the question, sir?
Sir, we can do.
Okay, is it, if it is not done, let us see the solution, right? So not sure.
So give 1 more minute, sir.
One more minute.
1 more minute.
Yes, sir.
We have to find the norm, right?
Yes, norm of this. Uh, So square root of the whatever the distance is, right, between these two vectors.
Sir, what is the formula for finding that is it is a gradient of L W naught?
Sorry, what is it?
Gradient of L W naught. I know the formula, but I was confused. But I did it wrong or right, I don't know.
What formula have you used?
Gradient of L of W naught. I think I have done wrong. So please आप
Okay,
formula
we'll
बता
see now.
दो एक
Now,
बार.
now anyway, we are going to see, right? In a minute, so we will see the solution there. Fine. Okay. Yeah, I think I'll go to the solution now. We, uh, is this the formula have you used? This one?
Yes, yes. We have equated 2
Yes.
into x into x transpose.
Correct. Huh? X is
2
transpose
into x into x transpose.
2. I think 2 is it not getting cancelled? If you, I think you use half into this, right? I think it's fine. That is also okay. You can use the 2 because when you do that, 2 will come out, right? That's it. That is okay. What formula is used in the lectures? Do you remember any formula?
Actually, like when sir was solving, he had shown 2 into x transpose into w minus 2xy.
Okay, it is not getting cancelled anywhere because sometimes people use half of this, right? But it's okay. It's anyway. It's average of it, right? Maybe your answer
Mm-hmm.
will differ a little bit.
This is correct formula, sir.
Okay, I don't remember exactly because I think that 2 should be getting cancelled somewhere. It's a similar thing, right? It's like y minus w transpose x, and you just have to do the derivative, like find out the derivative with respect to w. But okay, this is the formula, which is x transpose w naught minus
Actually,
x.
in the derivative, the 2 remains, actually, 2 stays.
2 stays. Okay, let me check.
Yes.
Then I need to see the slides. Sir has used. Okay, okay. Just a
I
minute.
don't know, maybe if it's a constant, if they have.
I remember thing is that like we use half to cancel out that 2 extra 2. Let us see. weak by that. This gradient descent. Right. Here, two is there. Okay, I think two is used here, right? Two
Right.
is working from x minus w to transpose
So in the question it is giving, we can use 1 by half, like half into uh, the error function, which will cancel this two.
yeah, okay, I think it is written here.
That is also yes, yes.
Yeah,
That will
fine.
cancel the two.
Yeah, so I think they have used generally people use two, or if they don't use also, because it's in the same direction, right? Whatever the w you will get,
Mm-hmm.
if you don't use half, or if you use half, what will happen? It will just shrink that vector, right? Anyway, you are getting maybe someone will get w, or someone will get 2w, possibly, right? But they are on the same line, so generally it does not affect the solution. This 2 is half people will take to avoid that 2 in the calculations. That's it. Fine. So I think that doesn't have any issues. But since it is given in the question, half, then you should use that half here to get that cancel, or to cancel this out.
Yeah, I didn't notice the half actually. Yes,
It's
sir.
okay. It's okay. No issues. Anyway, you are able to find out this formula and then use the calculations there, right?
Yeah, this is fine. Yes, yes.
Yeah. Probably
Sir,
your vector maybe is like this vector maybe 0.46, and
Yeah, no, no. Actually, I've done some calculation mistake. Yes,
mistake.
yes.
Okay.
Yeah.
Yes. Others, someone is speaking.
can you show the question?
Question.
Okay.
And now this was the calculation for the gradient descent. It's a simple one. Now we have used W naught. Just notice this one. This W naught is initialization 0, 0. Now when we calculate the gradient descent for, or stochastic gradient descent for the batch one is of uh, I said like it's a 2 samples. So you need to use that batch, and you can just notice that we are using W naught here when I am calculating this the first batch of the first iteration of this stochastic gradient descent, and you should reach to this value, which is the updated one, uh, after using the first batch of the gradient descent. And then if you use the second batch, notice that you are using this value, right, which is the updated one after the first batch in here, right? So that means I am actually not using 0, 0 again. I'm using what, the next whatever the updated value is there inside the iteration. And then you get, if I use this value, you notice the formula is same, right? The formula is same for that gradient descent and the stochastic gradient descent. The only thing you should be thinking about is that we are using the updated value, which was I have used it previously, and then I reached to this value. If I use this one, I don't think we should be using that. Oh, okay. So here, I think if you understand it, let us say we have started with uh, at this point, right? We are going into this direction by using the first batch, and that vector is 0.08 and 0.07. The next vector is but I need to use this value, right? That means this iteration, and then I'm moving to the some other direction, and that value is 0.1932 and 0.1632. The final value is by averaging these two values, 0.08 and 0.07, and then I'm
What
using
is the need to do half?
average. We are averaging the values here. So let's say if I
Is it in the formula for stochastic?
no. See, this is the stochastic gradient descent. So let us say you have let us say you have uh, 2 cross 100, right? If that is my entire data set, suppose, right? What is this dimensions? This is number of samples in that data set, right? Entire data set. I have chosen to have the 5 batches, right, of stochastic gradient descent. Let's say
Okay, so if 5 batches are taken, then 1 by 5.
1 by 5. Yes, 1 by 5,
Hmm.
and whatever the WSGD for the first batch plus WSGD for the second batch, and like that to WSGD for the fifth batch, and then you take the average of this, and that will be your WSGD. Fine, understand? But when you calculate WSGD for the first batch, you will be using the value which was obtained at the end of the last iteration, or whatever the, let's say you started with this initialization, right? Then you will be using 00 here. For calculating SGD of the second batch, you should be using the previous updated value, right? That is WSGD1 to calculate WSGD2. Okay, and then you can take the average at the end.
Who takes that decision to take the batches?
Huh? Sorry.
कौन डिसीजन लेगा कि बैच कितने क्रिएट करने हैं?
That is up to you, right? So how many batches you wanted to do? That is so generally.
So for this case, it's given in the question, right?
Yeah, in this question we said to have only 2 batches, right? Because by taking first 2 samples and the next 2 samples, the total samples are 4. So we have just divided this data set into 2 halves. So first half will contain 2 examples and another half contains 2 examples. So that means the batches are 2. Fine. It is up to you. So I guess you guys know what is the cross validation. I don't know whether uh, validation set have you encountered till now? Whatever your lectures you see.
So not in the lectures till week 5,
Okay,
but
week 6 I think it is there.
yes.
But matching it is matching.
So how many batches should be there? It has to be decided by us only, right? So how many?
So
Because
can you show the calculations for batch 2, please?
yeah. So this is batch 1, and for batch 2 it is this one.
Sir, shouldn't the gradient be 2 times of
Gradient. So this is
Okay,
what.
sir, इसके नीचे.
Okay, I'm going there. So this is for batch 2. That is the second half of the examples. This is what WSGD of the first batch, and then this is your batch 2. This is your corresponding Y, and then you do the calculations, and then you finally reach out to this part.
Sir, you mentioned something related to cross validation and this gradient descent in 2 batches. Sir, how are they related? Can you like brief us a little bit?
Not related as of now. See, I will talk. Maybe when I'll explain for week 6, right? I will just talk about that particularly there, because it is related to the hyperparameters, and how it is related. Once you understand the next part, right? Maybe you can be able to properly relate. Right now, if I talk about it, you may not be able to relate it like very easily. When I just speak about week 6, and then when we talk about this Rigi regression, right? That time it will be very clear, and then you
Yes.
can actually use it for any other terminologies, right? So it's not like the validation set is not only uh, applicable here. It is applicable like in so many cases.
Yes.
Whatever the upcoming weeks or the next deep learning, everywhere it is applicable. We'll talk about it there properly. Right?
sir,
Yes.
like shouldn't the gradient be 2 times of what you have computed?
The should the gradient be what? 2 times.
Hmm.
That's why we are taking the average, right? We have to average it out, and now we'll have to see how much far it is from the gradient descent and the stochastic gradient. Okay, so let us say how it is happening. So if I use the entire data set, your, let's say this is my WGD, because it's a vector, right? Let's say this is the direction in the WGD case. In stochastic gradient, suppose I will move into this direction. This is WSGD for the first batch. Then maybe you move into this direction, let's say, and after that you will reach here. Let's say WSGD of the second batch, probably, or okay, I'm just talking about the direction, right? I'm not just talking about the exact value, but they are actually moving into the same direction. The problem is there will be some maybe your gradient descent may have moved it a little bit further, right? So there, this is the final, let's say, vector. This is your WSGD, and there will be some
Sir, but
difference. The
sir,
difference.
but in this one, we are using the average, right?
Yes, yes. So yeah, so this is for the representation purpose. Generally, what happens? Let's say
Mm,
I use maybe this vector, right? This will not
mm,
be after this, right? The another also will have some other direction, and then you take the
mm.
average direction, and it may have certain maybe this direction, some kind of like that. Correct,
Okay.
right? So because vectors, when I talk about the vectors, right, or values, they will not, they will go through origin only, right? This is one
Mm.
point,
Oh,
right?
go through origin, yes, correct.
Yeah, this is one point,
Yes.
and this is also another
Okay.
point. So basically, if I try to look at this, one vector is this one, another vector is this one, and I'm going to take the average of it. Average, how will you take? You add this vector into this, right? And then I think you should use the parallelogram
Yes,
method,
parallelogram law.
right? So maybe this is the direction, right? I'm this is like, and then take, you take the half of it.
Resultant vector.
Half.
Resultant vector.
Yeah,
Okay,
this is the
half.
resultant
Okay.
vector, and I'm taking the half. In this half, when I say, that means is the average here, and this is your final direction. But your gradient descent might have this direction. Understand?
Okay.
Correct, right? Uh, I hope it is understandable. See, like
Yes, sir.
Got it, sir. Got it.
correct, right? This is maybe another direction. What you do is you take the parallelogram method, possibly, right? And this is the addition, right? And if I take the average, so this vector will be this, and this is your final WSGD. Correct. There will be some
Okay.
gradient into that direction.
So after T iterations, we do this basically, right?
Correct.
Okay, sir.
Okay.
But
So
taking
T
two
iterations means T batches, right, sir?
No, no, no.
T
So
batches.
no, no, no. Let's say for one iteration, if, let's say you have X as, I'm just talking about uh, 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 some example here. Let's say you have 100 samples. Fine.
Mm-hmm.
For first iteration, you have, let's say, 5 batches. I have divided it into 5 batches. So you have one WSGD for first batch, WSGD for the second batch, and like that to WSGD for the fifth batch, right? And then you take the average SGD, right? Let's say this is my average, which is WSGD 1 to WSGD 5 divided by 5. This is my WSGD after first iteration. Then my for second iteration, it will have another WSGD
Okay.
1, and like that 5. So entire, when until that entire data set is completed, right? This
That
is
Okay.
is
So
one.
in
yeah,
WSGD one, we are having a certain data set basically, right?
yes. Few
Sir,
examples.
And
then
again,
You'll be using,
yeah,
let's
yeah.
say, 20 examples here. So your data size is x 2 cross 20. Here it is x 2 cross 20. Like that will be like this.
sir,
So
according to
Okay.
this logic, then in the question we should have taken 0, 0 as for both the batches,
no,
right?
no, no. So you have to actually use it like this. So basically, it is not called as iteration. If in the case of mini batch gradient descent, right, it is called as the epoch. Okay,
Okay.
I don't know, some of you might have heard it. This epoch is very popular in deep learning case. So one epoch is uh, entire, like the iterations through entire data set. Fine. What we are doing is, in one epoch we go through like 5 iterations, kind of. So that's why they call it as, not call it as iteration, they call it as epoch. And under epoch, let's say you have 5 iterations. Correct.
Okay.
But in this course, sir have never used the terminology of epoch. Generally, in until the machine learning has developed, right, nobody has maybe have said this another terminology. But epoch is the epoch. One epoch is uh, the like passing through entire data set. And generally in deep learning case, we have this epoch concept because we have like huge data set and we can't use the gradient descent like entirely at one time. So we need to do it in many batches. So it is very popular
So,
in there.
so
Okay.
in this example also we have somewhat done in mini batch, right, sir?
Yes, yes, same mini batch. So you can say that one epoch of this in this question, right? One epoch, your data set was x2 cross
X1,
4, right? And in the first iteration, when you calculate WSGD, let's say if I say as epoch, then
2
WSGD
cross
was
2.
2 cross 2, and then WSGD x 2 cross 2. And when I calculate this, I use so initially I use W
Okay,
for this, and then I'm using it for here. If I go for the next epoch, the second epoch,
okay.
then I'll
So
be using
basically,
this one.
so basically whatever we have done in the first epoch only.
First epoch only, yes. Right. So
Okay,
like you done until first epoch. We need to go, and that is what that is the result of first epoch. Result is the average. Then you use the for second epoch, right? What you do?
You
So
take the average.
you use the WSGD average of the previous epoch to calculate WSGD of the first batch in the second epoch.
okay. So we will, okay, that will be the initiation, right?
Yes, for the second epoch.
For the
Initially,
second epoch.
yeah, for
Okay.
the first epoch, it was the randomly initialized values.
It was 0 0 basically, whatever we have.
Yeah, whatever you, it's not like required to be have 0 0. It can have any other.
Understood, understood. In this example, I said.
Yeah, got it. So whatever you have done
Yes.
in
Okay.
the first epoch, and that means because you only used one data set, right? Here, entire data set you used it only once, and that should be like nearer to the gradient descent, because in gradient descent in the first iteration itself you are using entire data set and you will be reaching to the some value, and this value should be like somewhere closer to the WSGT, right? That is our hope, that if I use the mini batches, I shouldn't be like deviating so much from the gradient descent. But since my data set, if it is very large, right, calculating the gradient descent will be computationally heavy because I need to do this all calculations, right? And that's why we uh, use the subparts of it, subparts of the data set. Okay, clear?
So how do we know how many iterations we need to perform?
No, so let's say you choose, let's say you have 100 examples, and you choose like 5 batches. Then how many each batch will have how many samples? 20. So that means in one epoch you should go through 5 iterations, right? If I choose 3 batches or maybe 4 batches, then each of the batch will have 25 examples, and you should be doing it till 4. You know, right? You know the data size, right? You know like how much data size you are having. That means you know how many examples you are having. You should just decide like how many batches you want to do it. If you have, let's say, 10,000 examples, so how many batches you want to do it? Maybe you want to do it like 2,500 in one batch. So that means you should be doing it for 4 times. If you have 2,000 in one batch, that means you should be doing it for 5 times. If you have 1,000 in one batch, that means you should be doing 10,000, sorry, 10 times in one epoch, right? That means 10 iterations in one epoch. All right. Okay. Let's move to the third question. Yeah. So consider the following data points for a regression problem. Okay, where Ci is a some real number and U is in RD and U is not equal to 0. Fit a linear regression model for this data set and find a predicted value for the test point X test, which is 5 times U. Fine, and we have given the provide like this information, extra information. Try to solve this problem. Okay, let's see this. This is a similar problem. It's just that you need to find out how to get this, the predicted value for this test point. So that means you should be finding out w hat first, and then the prediction will be w hat x test, right? So let us see how it can be done. So this is the loss, right? This is the loss function we are having, which is w transpose xi minus yi whole square. And if you do it for n examples, you should be summing out the square loss. Then you will take a gradient of that, and this is your gradient of this function, which is w transpose xi minus yi into xi. We know each of xi is what from the equation, which is
Ci into u.
to u, right? So some ci into u. I just plug in into this, and if you expand this bracket, if I take ci into this bracket inside, you'll get this w transpose u into ci square minus ci into yi into u, right? And this is your loss. You need to minimize this loss. That means you'll have to take the you will have to equate it to 0 to get that whatever w general you should get, right? In this case, you'll be getting this value, which is w transpose u as summation of I equal to n ci yi divided by summation of I equal to 1 ci square. We have given these values in the question, which is 20 and 100, and that means it is 20 by 100, which is 0.2, which is w transpose u. And what is your test point? Test is 5u,
5 dot u.
right? And what will be the prediction for this test point? Let's say y pred.
5 into 0.2.
W transpose, right? Or w hat transpose x test, right? Generally, this is your general uh, y prediction. This W transpose, we have learned it before, and you are using this learned weight vector to compute the prediction for this x test, right? Then that means it is W transpose x test is 5 times u.
5u.
So that means 5 times W transpose u. We already have found out what is W transpose u. I just have to multiply with that 5 into 0.2, which is 1. So the prediction will be 1. I hope this is okay. There should not be any issues till here. Then I just plug in the value of xi as c times or ci times u, and if I just equate it to 0, right? So this quantity to 0, what should I get? Basically, I think you will be getting this one, right?
Summation I equal to 1
to n w transpose
u.
u into ci square, right? And equal to
W transpose u.
summation of I equal
We
to
can take outside W transpose u, right?
W transpose u, because that's a
Yeah.
constant, right? It's a dot
Yes,
product
it's a
between two vectors. That means it's a constant value, right? W is one vector, u is another vector, and if I have that W transpose u, that means it will be a dot product between that W and u, and dot product will always be a constant. So W transpose u times summation of I equal to 1 to n ci square. What happened to this u? Since it is multiplied with this entire quantity, this u and 2 will go to 0, right? Because it will go to the denominator. So 0 divided by any positive quantity, it should be 0. And how should I say that it is positive? I think in the question it is given to me is that u is not equal to 0. So that means 0 divided by the quantity which is not equal to 0, that should be 0. And then you should get this 1 to n ci ui, right? So it is there, right? So I think it was fairly the simple problem. It's just that you should know the process, right? So always remember what is the loss function for regression, and you should be able to find out the answers. Maybe I'll take this question, maybe final question, or maybe I'll see one more question, and then we can go to week 6. The remaining problems you can see later on. Okay.
Sir, please upload this PDF also.
Yeah. So I'll just attach it to the calendar. Okay. Today itself, like after the session, or whenever we are in the session, after once this Solidus is over, right? I'll just attach it to the calendar
Sir,
itself.
also you can upload on the folder also.
Yeah, that also I'll tell the team.
Yeah. Okay.
Okay. Yeah. So this is a question regarding the kernel regression problem. So kernel regression with the polynomial kernel of degree 3 is applied on a data set which is xy. Let the weight vector be given by w, which is phi of x into this, right? Here phi of x is the transform data matrix, which is whose ith column is phi of xi. What will be the prediction point? Prediction for the data point 0, 0, 0, 0. uh, you, you should be able to understand. I think that there is one derivation, right, regarding the kernel matrix. You should be able to use that one. All the information is already here. You should have to manipulate that information to get the answer. Okay, I'll be giving you 3 minutes to solve this, and we'll see the solution.
Hello, sir.
Yes, done.
Sir, my query is, yeah, we have done that. So, अगर ये जो हमारे चारों पॉइंट्स जीरो वेक्टर्स दे रखे हैं,
हाँ.
so अगर ये वन होते तो
Same, right? What is the change in that? If it is one also, what how it will like, we just have to find it out, right? It may be
yeah, data points
1111. That's it, right? What is it? It doesn't matter, right? No.
does not matter.
How will it will matter? Like, so what is this? Like 00 is what is the dimension of this vector? X test
4.
4, right? So that means you should have 4 points, right? Because your data set is of uh, 4 dimensional, right? So each xi here is in 4 dimensions, correct?
Yes.
So it can have 111 also, right? It will be another vector. This vector x test is it in origin is an origin in 4 dimensional space, right? If you have 111, what does that mean? It will have let's say if you have 4 dimensions, each of the dimensions will have 111 as a point. So like what do you think, like what is your point in this? Like if it is 111, we need to find out uh, the prediction, right? The prediction will be different for that vector, don't you think? Okay, I'll give you the simple example for this, right? So okay. So we'll try to visualize in two-dimensional data set, right? So let us say this is your x and this is y. Y is what? The prediction, right? Or maybe the label which you need to predict. uh,
My query is the ये जो data point है ये test point है ना.
I'll tell you I'll tell you exactly what is this. Fine. Just what is, let's say you have 5 data points. Okay, this is, let's say 1, 0, 2, 3, 4. These are the 5 data points, which is 1, 2, 3, 4, and 5. What is the dimension of this data set? So x is the data set 0, 1, 2, 3, 4. What is the dimension of this data set?
5.
1, 1. These are 5 examples, no?
One.
This all data points are lying on x-axis. That means its dimension is 1.
Yes. Dimension is 1.
Right. Suppose the for x equal to 0, the uh, value of y is, let's say 1. For x equal to 1, the value of y is, let's say 1.2. Okay. For 2, it is maybe again 1. 3, it is, let's say 1.4, and 4, it is something some other value, right? So this is the value corresponding to 0, this is the value corresponding to 1, this is the value corresponding to 2. So this is the space which you are looking for, right? Now what you do is you have one line which is trying to pass it through this data set, right? And that line is what? Let's say it's w. Okay. But what does, again, what is the dimension of this w line?
4.
No, 2, right? How it is
Okay.
4? It's in two-dimensional space, right?
X and Y, yes.
There are 2 dimensions, x and y. All these data points are lying on to 1 dimensions, and this line which we will try to pass it is of 2 dimensions, right? Then you will have this, but it will have certain errors here, and by minimizing those errors, we have found out this is the best fit line, which is w line. Now what I'm saying is there is one more data point which is coming in here. Let's say that data point is 6, and this 6 is my x test. Fine. I need to find out what is the y corresponding y to it. So how will you find it out? We'll just uh, go onto this line and we see the corresponding y value, right? And that is my prediction. correct? This is the case only for the data which is in one dimension, which is x, the x and y pair that makes your total dimension of this data set, right, as the two-dimensional data set, and you try to find out this w, and now I use this w to predict the test data points. But imagine this data set is of not in the one single dimension, it is having more dimensions than that. We can't visualize that, right? We can just imagine that. So if your data points are in, let's say, two dimensions, how does that will look? Let's say we'll try to see that data set. So you have x1 here, you have another feature which is x2 here, and now your data points are like this. Okay, let's say these are the data points. Where do you think the labels of these data points will lie in? The third dimension, right?
Yes, sir.
Right, and then you try to draw a line through this, but will that be a line or will that be a plane?
Plane.
Plane, right? So it will be a plane, and then that is what the plane is. But then you have one more data point, which is the test data point. It can be anything. Let's say if the data point is here, so the data point will have how many dimensions? Two, right? It will
Two.
have zero. So two values. If the test data point is here, what is the dimension of this data set? Two, right? But the values are 0 and 0, correct? Like this four values says that this data set, right, or the features space, we'll call it as feature space, because x1, x2, x3, x4 will be the features, and the feature space is of like what are the dimensions of this feature space? It's 4. So it will be a 4-dimensional data set, and this 0 0 0 0 is the origin of that, right, of that space, like this. X, this corresponds to the coordinate of x1, this corresponds to the coordinate of x2, like that it will have. And now you try to predict for the test point, and test point can be anywhere. So in this case we are saying that the test point is 1 1, and what will be the prediction then? It will be W transpose, because W is the line which you have learned, right? The vector which you have learned by during training, right? So whatever the examples we had, we learned it from there, and now we are using that to calculate the value, the prediction for this. Similarly, you have this 4-dimensional data set. I need to find out what is the prediction for it, and how to do that. This you know. What is this case?
Kernel function.
Yeah, but what is this? Basically, it is W transpose phi of x test, right? This is what the prediction, right? This we are
Sir,
doing.
these formulas are not given in exam. Why?
What is it?
Formulas नहीं होते एग्जाम में जैसे स्टैट्स में होते थे.
It will be given in the questions, right? This is anyway. This is solved with us, so not given in the question, but in the question paper it will be given. For this.
Okay.
Yeah. So and what kind of kernel functions we need to use it here?
Polynomial.
Polynomial. So I'm using the polynomial function, and okay. So how will you use it, right? So that also you should know. Will be k of x test and xi, right? What is xi given to me? This one is the xi, right? Correct.
Yes, sir.
This is the weight, right? This is the alpha, right?
No,
Oh,
this is
yeah.
alpha and alpha star.
This is alpha, right? So
Correct.
Where is x given?
X is not given
X
to
is
xi.
X is not given because
xi.
all are zero na. That's why
Correct. So we don't need
X test is
exactly.
zero. We don't need
So because even if it is not given to me, this value will be what, 1, right? Because let's say okay, I need to
yeah,
find
1
out.
plus 0, everything will be 0 basically.
Yeah, it is 1 plus
0
x,
whole cube.
x test transpose xi, right?
Yes.
And to the cube. But since x test is 0, the multiplication, the dot product will always be 0. Here it is 1 plus 0 to the power 3, and then that means every time it will output what, 1, right? This kernel function given to me, so everywhere it is 1 1 1 1, and then I just use alpha I. Alpha I is given to me, and into this one.
Sir, I have one doubt. Why? I have understood the kernel function one that is x test, but one thing it is one multiplied by one because of the kernel function, or
1 multiplied by 1. Where is it? 1 multiplied by 1. Where you are saying?
no?
Here.
We have multiplied the that is w with one by.
Where is this w multiplied? Here it is alpha, no? Alpha
Alpha, yes, and alpha is multiplied by one by.
1 we have found it out, right? Okay. What is okay? These are alphas. Do you think this is fine, right? This alpha. What is your alpha vector? 1.3, 0.6, minus 0.2, and minus 0.7, right? This is what alpha 1. This is your alpha 2, alpha 3. This is your alpha 4. Okay, is that okay?
Yes, yes.
Then this is your vector, which is x test vector, which is 0 0 0 0. Fine. Okay. Then I need to find out this case alpha I into kernel function, right? So this is what x, this kernel function, it is applicable point wise, right? Because it is in summations, right? So it is summation across all the points possibly. But here, if you think about it, is x transpose y. So your vector is x test is 0 0 0 and 0, correct? And your another vector x may be what, some values will be there. We do not know what are the values. It is x1, x2, x3, and x4. Okay. If I take the transpose of this, what I'll get? Or if I do this multiplication, x transpose x
Single
test
row.
x. So, but it will be 0, right? Whatever the values of x1, x2, x3, x4 does not matter. It will always be 0, right? Because 0 is multiplied with this, right?
Okay, X transpose test.
Hmm.
So
Of
why sir अभी मैंने यही क्वेश्चन पूछा था आपसे जहाँ पे हम 0 के बजाय 1 लिख रहे थे तो आपने कहा कि कोई फर्क नहीं पड़ता.
no. The value will change, right? Otherwise, the calculations will happen smoothly, right? But then I need to know this x1, x2, x3, x6, x4, right? The values there for the data set.
हाँ मतलब चेंज हो जाएगा ना मतलब but we are saying कि it will change ना the values will change
Right,
the
definitely it will change, right? It should change. I have given that entire diagram, right? It is like if you change it, see, if you have all these data points, suppose, right? And if my W is going through this, fine. If my X test is this point, suppose, right? Or maybe let's say this is X test. What will be the Y? Corresponding Y will be this one, right? But if my X test is this one, will that change my Y prediction? Yes, right?
yes sir, yes sir. So मतलब value change हो जाएगा बस ठीक है I got the point.
Yeah. Right. So here, since it is 0 everywhere, it is not, and if you pass it through this polynomial function, it will always output as 1. So 1.3 into 1 plus 0.6 into 1 minus 0.2 into 1 and minus 0.7 into 1. So finally, you'll get the answer as 1.
सर क्वेरी इज अगर 1 1 1 हो जाएगा तो आंसर कैसे निकलेगा हमारे पास तो x1 x2 x3 x4 ही रहेगा ना
Then you should have that value of xi, that another vector I should know. The data points, data set we should know.
सो हमारे पास डेटा सेट तो नहीं गिवन ना
So see, for this particular example, we don't need data set since your x test is 0 0 0 0. If it is 1111, then I should know what is the X data set is. Correct?
Okay, fine.
See, this is one numerical, right? But in general, we shouldn't have like this, right? We should be coming to this W based on some data set. Right? You should have that data set in prior. This is a numerical, and hence it is not required. That's what. Okay. Okay. This is the last question from this topic.
Sir,
Yeah.
sir, also in the polynomial kernel, like
Hmm.
since we use, xi transpose plus one whole cube, right?
Hmm.
So this, sir, so how do we decide on this constant? Like, is it always one or
No, it is.
axy, sir?
It depends on what kernel you need to use, right? So it's not like you can use Gaussian kernel, you can use another kernel. That is the choice of yours. See, all of this
No,
is
no,
like
correct. Here we are given, about the kernel,
polynomial kernel.
basically,
Okay.
polynomial kernel. But in case, this, I'm asking about this 1 plus x transpose y whole cube.
No, it can
So
be
this
two.
1,
Yeah, it can
2
be two.
also, right?
Yeah, it's just it should have polynomial. That doesn't like
Understood.
this constant can be anything. So this is the this form c plus xy or x transpose y, whatever the like if it is 2-degree polynomial, it is 2. If it is 3, it is 4, like that. So it
It
should
can be
be
x transpose y whole cube also, right, sir?
x transpose. Yeah. Then c can be 0 also. That's fine.
So it can be 0 also, no?
Yeah. That will like then if that is 0, then what will happen? Let's say simple thing. It will be xy cube, right? Then this polynomial will be of x cube plus I think 3 or x cube.
3xy squared plus 3y squared.
No, I think it will not be right.
No,
Because
no. X1, X2, it will depend, na, sir. You
y
like.
cube only. This will be a curve until I add some constant in here, right? Then this is a plus b whole cube, right? A plus
Right.
whole cube. Then it will be a cube plus 3a square
B
b
cube
plus
plus
3b
3b
square a plus
plus
b
B
cube.
cube
So you should have something in here. So either you can use some constant, right? So
Understood.
some constant has to be there. It cannot be 0. If that is 0, then it is like a cubic function only. That is x cube
Cubic
y.
function.
Okay, sir.
Fine. So let us finish with this fifth question, and then we'll see maybe 20 minutes. I'll talk about week 6, and then we'll continue on Sunday. Okay, this is the data set you have given. What is the projection of the label vector onto the span of the features is 2, 11, and minus 8, and predict the label of for this 7, 3 using the linear regression. So each of data point is of how many features here, or what is the dimension?
2 dimension.
2 dimensions. Yeah, and this is what your this is what is the projection given to me on the span of feature vectors, and this is your text point. Text. Now you'll have to solve it.
Sir, why this is 2D?
Yes, what are you saying?
Yes. What is why it is in two dimension? Is it independent vector? Okay, one by okay.
Two, right? So this is like this 1 2 3 1 and minus 1 4. These are the three examples given to me, right? So let's say this is x1, this is x2, this is x3.
So x1 and x2 are linearly independent. That's why, na?
Yeah, you can say that, but in general, yeah, if you think about it, like all these three are not dependent on each other. So anyway, but if you see it also, right, the span of these two, like all three vectors, also it is three dimensions only. No, sorry, two dimensions, right?
Due to
But
linear combination and all thing, na?
correct, but if it is not also, let's say if they were dependent also, they were in a subspace, but under a space of like two-dimensional space, right? They will form a subspace. They will not form a space. Currently, they will form a subspace of two dimensions, right? Even they are linearly independent. Okay.
So we can continue with the answer, sir, if it's because time is very less.
Yeah, just I'll wait for some time, like maybe someone is solving this. I'll take like maybe more, 2 more minutes and then we'll be solving this, seeing the solution. Right? Okay, let's see the solution. I think only uh, one answer is there. Okay. Is this correct? Uh, this is this is familiar to all of you. What is X transpose W should be equal to Y prediction?
Yes, yes.
This is okay, right? So I know X. I know what is X. Your data set is, it was 1 2 3 1 minus 1 4, right? And this X transpose W should be equal to the prediction, right? So I have this Y's, corresponding Y's. Do we have that? Yes, right. It is 2 11 and minus 8. So X transpose W should be equal to Y prediction. That means I need to find out what is the value of W1 and W2. Will you be able to solve this equation? Yes, because then this equation will be W equal to uh, What is it then? X transpose
X transpose inverse
X
into
transpose inverse into Y, right?
yes,
By this matrix vector equation, right? So,
yes, yes, yes.
and then you just have to do uh, X transpose inverse into Y. So that means I need to find out this X transpose first, and then I think I should be taking the inverse of it, and then you can just solve it for it, right?
But
Uh, but I think
this
still, can you be able to find out X transpose in this case? X transpose,
no, no,
no.
no.
Why? Because the dimensions are
It's
not.
it's not a square matrix.
Yeah, so you can't find out what the
X
uh,
transpose inverse. You have to go with X transpose inverse.
determinant, right? And that's why you
Yes,
need
yes.
to solve it for what? This one. What is that? Then it is x transpose inverse xy. All right. So I have x. I have so you know this y vector. You know this x transpose. That means you know x. You just solve it, and you will get this y1 by sorry w, which is w1 equal to 4 and w2 equal to -1. And what will be the prediction then? It is w transpose x test, right?
W transpose X test.
And what is w transpose? Is 4 minus 1.
4 and -1.
It is 7. So it is 28 minus 3, which is 25. And that should be your answer. Okay. Fine. So I will. There are few more questions. Maybe you can just. I'll attach this to this session as well, and then you can see at home. Any doubts if you have, maybe we can take in the next session. If you have any doubts in this, uh, uh,
Sir,
any questions, right? Yeah,
XX transpose inverse into XY will not work.
that will work only, right? So that's what. Uh, Otherwise, you can't find the solution, right? So you need to do that. So you will have to use this only, this formula. This will help you in understanding what is y, right? So what is the prediction of y or y predicted, and this is your x transpose here. So anyway, that will work. You just need to find it out that way only.
Okay.
Okay. So I'll just stop it here for week 5. Maybe we'll start with week 6. So I don't think many of you have watched week 6 lectures, correct? So I will just start. Maybe I will describe it for maybe 20 minutes, and then I will ask you to go through the lectures maybe by tomorrow and come back on Sunday. We'll continue week 6 there, and we'll solve some questions on that Sunday session as well. Okay. So linear regression idea is clear to you. I understand that till now it is fine. Like other things in linear regression. Do you understand week 5 from the lectures? How this derivations came and everything?
Yes.
Yes. Okay. So how did you find the W hat? There are two ways. One is calculus way. Another way is what to find out this W hat, the solution to that problem. Any particular method we have used?
Gradient.
Hmm? Maximum likelihood. Have you seen that method in week 5?
Yeah.
Posterior into maximum likelihood.
So how you use that? You know, right? And the solution given by the maximum likelihood method, uh, is it the same as that of you have found out by using the calculus method,
Yes.
right? So that, but
In
how
case of Gaussian,
right? So why it is, uh,
So
or
we
why?
want to like
Sorry.
we like wanted to analyze some properties of the estimate we get, so
Correct.
that we
Correct.
can get to know how good is the estimate finds.
Estimate, right? So we should know that, and I think we, if you guys remember it from stats 2 days, we have some parameters to, or we have some techniques to analyze how good is the parameter estimated, right? What are those techniques? Can you just recall it? One is
Bias,
bias, yeah, bias, then variance,
risk,
hmm. And I think there was risk, right? Risk was,
Risk.
I think it was the sum of the bias square and the variance, right? So all of this will help in here. And what is bias?
So the error.
the difference, error difference.
Error is correct,
Error.
but what error? Like between what quantities?
The expected one and the
Yeah, it is the expected, or it is the difference between the expected value of the parameter and the true parameter, right?
true parameter.
Do you remember that?
Bit, sir.
Okay, fine. Maybe I'll just recall it in here. Maybe I'll just share my screen, because that is what we are going to uh, see today. So I think all of you have done stats to like very long back, and that's why maybe difficult to recall. But let us say we have these three quantities. So first place, how was that equations were like x1, x2, and we had like xn, right? What are those? The samples, right? From some, let's say, IID X. What is this? This is the population, right? Uh, so we
Yes.
are saying that there we have taken some samples from the population, and it will have some parameter, right? It may have W1, W2, W3 like that, or theta 1, theta 2 like the. These are the parameters we are having. Let us denote. Let's say these parameters are W. Okay, fine. Uh, I hope you all of you remember that. And how you used to find out this estimator parameter estimators? So there were, I think we have seen some techniques, which is one is method of moments, that is MME, right? Then I think we
MLT.
had MLE,
MLE.
which is maximum likelihood estimator, and third one was, I think, one we have seen
Bayesian estimation.
Bayesian estimator, right?
Estimation.
There were like the commonality between MLE and Bayesian estimator. Uh, we will not think about MMA as of now, but there is one thing which is MLE and Bayesian estimator, right? But what we have talked about this estimator, like, okay, why we need this estimators? First of all, parameter estimator, or these are called parameter estimation technique. Why we need these techniques?
Getting a better predictions.
No, but why we need, let's say, I know these samples are coming from this population, but I do not know, and you know, any data set, right, or any population, it will be distributed with respect to some distribution, right? Some known distributions, or let's say known distribution if it is there. Let's say these all data points are distributed according to Bernoulli, right? Or if these distributions are coming from, let's say if it is Bernoulli, then what parameter it will have? How many parameters it will have?
P and
P.
1
P.
minus P.
Only P, right? Only one parameter
P.
will be
P.
there. Correct. And these parameters, they, if I know this parameter, I can actually draw a distribution, right? Because that will decide the shape of the distribution, correct? And how it will decide?
Yes.
It can tell me about the mean, and it can tell me about the standard deviation of that
Standard
distribution.
deviation.
And that from only one parameter, I will be able to understand how my data is distributed, right? Suppose if I say IID, let's say normal, right? In that case, how many parameters we have? Two.
Mu and sigma.
Sigma square or sigma, right? The two parameters. One is mean and another is variance, right? So if I know these two parameters, I will be able to understand how these samples are coming from the distribution, right? But this is what my population distribution is. Do I know exactly what are these? What are the samples of, or what are the parameters of this distribution? No, right? Because I do not have any idea about
No.
the population. I'm just assuming that these are coming from the population. But then with the sample which is given to me, can I able to predict or predict about the parameters, right? And for that these techniques are used. uh, Based on the sample, can I be able to estimate the parameter? So whatever the estimation we will be having, will that be a true parameter or will that be a estimator of that parameter? Just an estimator, right? That will not be a true parameter, correct? So what will be the if you recall, what was the MLE estimator for Bernoulli distribution?
The mean.
Mean, right? So it is like x1 x2
Sampling.
xn divided by
Sample mean.
n, right? And that sample mean, uh, okay, let's I think it was, we used to denote it by
X
x
bar.
bar, and that is equal to p hat, right?
P.
Used to have that symbol p hat. What does that p hat says? Is it the true parameter of this population, or it's a estimated parameter? It's an estimated
Estimated.
parameter. So
Estimated parameter.
there may be chance that it will vary, right?
Yes.
It is not, because if I change the sample, right, will this parameter change, or will this estimator will change?
It may
Yes.
change.
Yes, right. Let's say if you have 1 1 0 1 1, this sample it is coming from Bernoulli P. What will be the p hat value? It is 4 by 5, right?
Yes.
If I have a sample, let's say if I have another sample which is like this, and it is also coming from the same distribution which is Bernoulli P,
3/5.
it is p hat will be 3 by 5. That means if my sample changes, the estimator value will be changing, right? So that means this p hat is a constant or variable?
Variable.
A variable. That means it will also have some distribution associated with it, right? Correct. Right. And whatever, like maybe this parameter is a variable, right? Do you agree that parameter, the estimated parameter is a variable, correct? And if I take its expected value, then that means I have,
Constant.
this is constant value, right? Correct.
Yes.
So if I just, and what is the true parameter here? P.
P.
So how much it is deviated from the true parameter, that is what given by bias. Okay.
This is also the distribution, ना? ये भी एक distribution ही तो है.
Bias is not a distribution. Bias is like, okay, so suppose p hat, right? It is distributed according to normal with mean as, let's say, 1 and standard deviation as 1. Is it possible? It's possible, right? If you have 30 samples, 30, so this is one sample, this is another sample. So if you have, let's say, 30 such kind of samples, you have 30 these values, right? P1 hat, let's say P2 hat, and like that we have 30 values. And if I draw a curve, right, or if I just plot all of these values, it let's say it is going according to this normal distribution, then it is expected value of p hat will be what? Equal to 1, right?
1.
Yes. Yes.
And
Yes.
standard deviation is equal to
1.
1, or
1.
variance also is equal to 1, you can say that. So that's how so this value what we are saying is this is the closest one to the true parameter. And when we say that it is this parameter, right, p hat is unbiased parameter, or it's an estimator, unbiased estimator of the parameter. It is unbiased
Bias is 0.
when bias is 0.
Bias is 0.
Bias is 0, that means the expected value of this
Is
variable
2P.
is equal to the
True parameter.
true parameter. So what we are saying is the p hats, whatever you are getting, right, if I take the expected value of that, that should be equal to the true parameter value. Is that correct?
Yes.
I hope you understand this part. This is very important since we are going to see some of the properties of this bias, this parameters, right? So in our linear regression case, what was the W hat we have got?
X transpose.
Was X transpose pseudo inverse or inverse XY, right? And we said this is what? This same as that of the W hat ML, correct? Agree? So W hat ML is what? It's a parameter estimator for W, right? The true W. It is not exactly true W, but it is a parameter estimator for W. And this is what? This is not a constant value, this is variable, correct? And it will have its own distribution. All right.
Yes.
So okay, that's fine. So in this case, maybe we can, so there are two ways to treat this, right? So if I have uh, so okay, let us understand this way. Maybe there is there is some difference between the MLE and uh, the Bayesian estimator, right? So what is the difference between MLE and the Bayesian estimator?
A Bayesian estimation,
It will have
we are
bias.
not sufficient with the like observed data. Like
Yeah.
we want some
Correct.
extra prior belief.
So we do not have any prior beliefs about the parameter, right? In MLE.
In ML,
And in Bayesian estimator, we have some prior information about how this actually W hat or W or this parameter uh, is like or what you can say is affecting the generation of the data set. Okay, so in MLE, how, let us say these labels are generated. Let's say we are saying that y given x. So given that x, how these labels are generated are given by what? W transpose x plus some error, right? Okay.
Epsilon.
Correct, right? Let us say you have this data set, correct? And if I wanted to draw W, say this W, correct? Uh, so let, for example, let's say I'll just focus on this point, okay? Just focus on this point. Maybe I'll just. So what is the so is this a true value of true y, right? For this, maybe this is y and this is your x. Now for this given x, this is the true value of y, correct? But what is the predicted value of y? Or is there
It's
any?
on the W.
So it is basically, it is W transpose x plus
Plus epsilon.
some error, right?
Some
error,
noise.
some error. And this is for epsilon 1. Let's say it is W transpose xi plus epsilon 1, which gives me yi, right? Or y1, right? So can I say that the total y's will have certain errors associated with it, right? Or can I say that the summation of I equal to 1 to n will be equal to what? Yi
Plus
y
AI.
minus W transpose x is, right? Is it correct? This is x1 y1.
सर ये EI क्या है?
This epsilon is the error. Okay, I'll just maybe I'll tell you. Let's say this is your data set, correct? This is your,
It has some error. I got this.
this is x.
YI is the predicted one. Na?
No, this is a true one. It's not prediction.
Okay, it has some error and then we just transpose.
So let's say this is your W. Is that okay?
Yes, sir.
For this point, let's say this is x1, correct? And this is y1. What is the predicted value here? for this x1?
W.
Uh, is this one? This is a prediction, right?
Yes.
Y1 prediction.
Yi minus yi is ai.
Correct. So basically this is a, and there is some error here. Correct?
Yes.
Right. So if this is the error, suppose basically this will not be like this, right? I think we will be taking the projections, because that is going to be your I think minimum value or something like that. But just try to understand this part. Oh, sorry. This is what your actual y1, right? And this is your prediction one, predicted one. What is the predicted one? W transpose x1, right? This is my y1 hat. We denote it by y1 hat, right? So it is y1 hat. Okay. And what is the error? Error was y1 minus y1 hat. Is that okay?
Yes. Yes.
And that is nothing but y1 minus w
W transpose
x1. Okay.
Yes. Sir.
And this is what your epsilon 1. Correct. But there is so let's say for this data point the actual y2 is here, but it is predicted here, right? This one.
Plus, yes, we need to plus that.
Plus is not required, since we take the squared error loss, we actually try to get it like
Absolute values.
Right.
Okay, cool.
So these are all errors, and if you sum all these errors, basically you will get this kind of relation. Is that correct? Okay. So if I just use this as let's say, that means I have observed some data, and based on that data, how these labels are generated. The labels are generated like this: W transpose X plus epsilon. Is that okay? Can I generate, if I have, let's say, x1, x2, x3 values, x1, x2, x3, and like that? If you have n values, can I generate the corresponding labels y1, y2 to yn? Is that possible if I know w and epsilon?
Yes.
Yes, right? If I know w and if I know epsilon, then I can generate these labels given the data points. And how they are generated? With this, right, relation with w transpose x plus epsilon. Let us say now I assume that these errors, they are distributed as per the normal distribution with mean mu and variance sigma square. All right. This is the
Yes.
this is the assumption I am talking about. Okay. This we are assuming
Then
that.
sigma also be 0, no? I think.
Huh?
If it is mu is 0, then sigma is 0.
Which sigma? Which sigma you are talking about?
That is sigma square variance.
No,
Is
no.
it?
Mean is,
It is.
why it should be, let's say it is normally distributed with mean 0. Will that the deviation will be 0 or not? No, right?
Yeah, deviation can.
If the deviation is 0, that means how can it will be normally distributed? It will be like the straight line only, right?
Okay. Okay.
Deviation, then it will not be normal, right? So normal distributed with some sigma square, that means that bell shift has to be coming, right?
If something is mean is middle value, na? So if
Yeah,
everything is
mean is the middle value of this distribution. Okay. Okay, let us say 1 minus 1 minus 1. Let's say this is the data set, simple data set, minus 1 minus 1 0 1 1. What is the mean of this data set? If I, this is a one dimensional data set, so there are 2 points here, right? Suppose this is 0, is 1, and this is minus 1. Let us say how many data points are here? 2, correct? And there are 2 data points here, and there is 1 data point
one,
here. What is the mean of this data set? 0.
0.
But what is the deviations? Deviation, how will you calculate deviation? Let's say this is x1, x2, x3, x4, and x5. Will the deviation is 0 or will that be different? So how do you calculate the deviation? It is x1.
Xi minus x1 minus mu whole square.
No, that
Plus
is the
x2 minus
square, right?
whole square. Yeah.
Yeah, and if you just wanted to see the deviations, it will be this one. So if I take
Under
this one,
Yes. Whole square.
so it is
Square
1.
root it will be. No?
Yeah, it is 1 1. Yeah, let us say, yeah, under root, correct.
Yeah.
So it is 1 1
1 plus 1. 0.
0 1 1,
1 1.
and then the total deviation will be how much? 4.
Root over 4. Root over 4 by 5.
xi minus 0
So first of all,
minus 1.
It will be 2 by 5, na, sir?
it is total, right? So it is 4. So basically, it
4.
will be summation of all, right? Summation. This is
Yes.
summation of all division squares and divided by
N.
Sir,
n.
there will be a square root also, na, sir?
Yeah, there will be square root.
Ah,
All right. So,
Yes.
but
2 by
is it
root 5.
0 or it's not 0? It's not 0, right?
No, it's not 0, sir. Not 0.
Something not 0. Yes.
So like this here also, if the some deviation is there, but its mean is 0. Mean can be 0. If the mean is 0, that doesn't mean that everything is 0 in this case, right? Okay. Now back to our point. Let's say y given x is equal to w transpose x plus epsilon, and suppose epsilon is distributed as 0 sigma square. What does that mean? This is a random variable, right? Epsilon is a random variable, correct?
Okay.
Right. Is x is a random variable or not? No, right? Because we know the
No, no.
all values I know, right, about x. Correct.
Yes.
Yes,
X
x
y
is
z.
known, sir.
W is also known to you or no? Yes.
W transpose, yes.
Correct. So W transpose x will be a constant anyway, right?
This is y है ना, so y तो पता ही है ना, y है.
No, no, we are generating y now. We know x, we know w, we know epsilon. So can we generate this? That is what we are trying to see. We know
Yes,
why.
we can.
See, in reality, we know why, but we are trying to understand the properties of the estimator. So for now, just think about it like I have x, I have w, I know the distribution of the errors. Can I generate y's? That is the question. And yes, I can generate. So in that case, if this is a variable, this is a random variable, and if this is a constant, so y given x will be a random variable or not?
Y given x is, please repeat what is it is.
So epsilon here is a random variable, right? Hmm? Because it
Okay.
is distribution, it will have this distribution. This is some constant. Then y given x will be a random variable or not?
Random variable, yes.
That will be random variable because
Yes, we are adding random variable.
right. So then it should be random variable. Then what will be the distribution of this? What is the distribution of y?
E से, yeah, डिस्ट्रीब्यूशन ई से निकलेगा इसका भी.
So it is a translation property, right? So it will be distributed as normal because epsilon is normal distributed with mean 0 and variance sigma square. And okay, I think I'll tell you this thing. Let's say y equal to a plus x, right? And if x is normally distributed with mean 0 and sigma square, a is some constant, what will be the distribution of y?
Yes, 0 sigma
Normal
x.
a and
Yeah.
square, right? Okay, how do you calculate it, right? So it is like expectation of y will be equal to what? Expectation of a plus x, correct? A is some constant. Then by the properties of expectation, it will be expectation of a plus expectation of x. Expectation of a is what? A. And what is the expectation of x? 0.
Sigma square.
So what is the expectation of y? A. Is it okay? Are you able to recall it?
Okay.
Huh? And how to find out the variance of y? It is variance of a plus x, and I can actually use the property.
Variance of a plus variance of x.
So basically, it is variance of a,
A plus.
variance of x. But if what is the variance of any constant?
A.
No, variance of any
Oh, it
constant.
will be, sorry, it will be zero, no?
0, right? Because there is
Variance of A is 0.
yeah, because A is a
It's a
constant.
constant, no?
Variance of any
Okay,
constant
okay,
is
okay.
0, right? I think you guys have like totally forgot the
Yes,
steps.
sir. It will be
Correct.
Little,
So
little, sir, little.
yeah. So variance of any constant is 0, right? See, if you have the variance, if you have the 5 constants, what is the mean? 5, right?
5.
The variance. Is there any variation over this data set? No.
No,
No.
there is no variation.
0.
0.
So for any constant data set, the variance is 0. And then what is the variance of x?
Sigma square.
Sigma square. So what is
Sigma
the
square,
variance of y?
yes.
Is sigma
Sigma
square.
square.
Sigma square.
So then what is the distribution of y? It is normally distributed.
0 comma sigma square.
No, a. Expectation
A
of
comma sigma square. The mean has shifted, na?
mean has shifted. This is translated, right? Okay, this is the translation property. Uh, the mean has shifted by that constant, but variance will be unchanged in case of this translation. See, I hope you should have understood that affine transformations. Okay, if you don't remember it, just go back to stats 2. There are slides regarding this a plus x, y equal to ax, and y equal to I think it is ax plus c. So these are called affine. This is affine transformation. This is translation, and this is the scaling, right? This translation, this is scaling, and this is
So translation is a property, right?
yeah. So in translation, what happens? The mean will shift by that constant. In case of scaling, what happens? So y will be normally distributed with what happens to the mean?
A
A
into expectation of x.
Yes. So it will be like multiplied, right? The
Multiplied, multiplied.
but what
Yes.
happens to the variance?
into x. Is it
A square. A square.
A square
A square into variance.
variance,
a
right?
constant square?
And it will
Okay.
be like the combined effect of this. So it will get translated plus it will get scaled the mean, right?
Scaled.
So it will get translated by amount C and it will get scaled by amount A, right? Then the mean of y will be in this case, it will be A mu plus,
A into expect. A mu plus C.
C. Let's say if mu is the mean, right? And what happens to the variance?
A square into variance of x.
A square into the variance of x, right? So so you if you I don't know if you guys remember. If it is not, you just go back and see that, right? So in this case, in our case, what do you need? See, all of this will be important throughout this MLT from here onwards, right? From week 5 onwards, all this MLE, Bayesian estimators will be very important. So now I am saying that y given x is a random variable which is like w transpose x plus epsilon, and epsilon is normally distributed with mean 0 and uh, uh, variance sigma square. This is some kind of a constant. So what will happen to what will be the distribution of y given x? It will be
We have calculated
normally distributed with how much it is translated? Mean
a square.
0 plus
Mean is epsilon.
no. Epsilon is the random variable, right? This is a random variable.
0 plus
This constant.
W trans.
Yeah. So it will be W transpose.
0 plus W transpose x.
So this is your mean. And what will be your variance? Variance is unaffected by that constant. It will remain
Unaffected.
sigma square. Is that okay? Hmm?
Yes.
Right. And we have seen that this W is the solution, right? For the linear regression case, it is done by W hat ML. So this is the maximum likelihood solution. Okay. Now,
Okay. Okay.
so this is a true parameter actually, right? This W is a true parameter. This is the estimator we are able to find it out. Is that okay for this distribution? Right?
estimator, no?
This is MLE estimator, right? This is not the MLE estimator. This is what your true parameter is. Then how will you find out its bias? Bias will be expected value of W hat ML
Expected to
minus W.
minus W.
This is my bias, right? But there is risk. What is the risk? Okay, what is the variance?
Sigma square.
No, in this case, it will be W hat ML minus
Achha. Minus
W whole square, right?
whole square.
Yes, whole square.
I don't know whether you guys are
Divided by something or not?
Yeah.
no, no.
Take an
Expectation of x.
expectation.
X square minus expectation of x square, right? Basically.
What is it?
Expectation of basically x whole square minus expectation of x square minus expectation of x whole square, right? We are following that only, right?
Minus, yeah. So general case, I think if it is x minus mu, right?
Yeah.
Yes,
Okay,
yes.
okay. In that case, what will be the variance in this case? X minus mu to the whole square, right? The expectation of that.
This
Yes.
is variance.
Okay, maybe I'll just my pages are over here. Load it. Okay. Let us say, okay, till now what we have seen is y given x is a random variable which is distributed with respect to w transpose x and sigma square, right? We have agreed to this part. W is my true parameter, right? And W hat ML is the parameter estimated by using the MLE, right? So MLE estimator, right? Or maximum likelihood estimator is my W hat ML. So we need to see that how good my W hat ML is, right? This is a question we need to ask, right? So generally there are, I think we have seen that there are few methods we can see that it is one is bias, and there is variance, and there is a risk. Is that correct? These three methods we know from stats 2 that can be used to decide whether this estimator is good or not, right? So
Yes.
so and what is which is the random variable in this case?
X, W transpose X.
No. That is okay. That is different. Leave about like now. Don't worry about that. We know that this is a distribution, and in these two cases, W and W hat ML, which is the random variable? Okay. Okay.
W hat ML, na?
Fine. Correct. So first place, okay, that is true. W hat ML will have certain distribution, right? And that is
Yes.
okay. That is again that is a random variable. Here also, what is the random variable here? This y given x, right? That means the labels are the random variables, right? Here, these are
Yes,
the
sir.
randoms. Okay. Now, if I wanted to find out this quantity, what is this quantity? Can you just tell me expected value of, say, norm of, let's say, W hat ML minus W to the whole square. Okay, just give me a minute. Let me show you one thing. Maybe if you guys have forgotten, let's understand it. Relation between uh, risk, bias, and variance. Okay, I don't know whether it is. If it's not there, then I'll just write it down. Somewhere it has to be there. Okay. Have you seen this kind of error? This is what it
Yeah,
is.
yeah, we saw it.
This is
That's true.
risk, and this is what variance, right?
Yeah, variance plus bias square.
And this is your chi-square. So what is your variance? So if I just write, okay, I'll just write it down. Okay, maybe you guys can just look at it once. Uh, do not worry about this p thing. Just think about this. What is theta hat? Estimator. What is theta?
ML is
Yeah, theta
uh,
is true parameter.
true mean, yeah.
And what is this variance? Theta hat minus the
Expectation
expected
of
value of theta hat, right? Because that theta hat is my variable, correct?
right,
That is what actually what you do in variance generally. It's a variation in the random variable, right? Or our
right,
general terminology is variation in random variable. But how you find it out? You just find out it's the square deviations, and you take the expectation of it, right? Expectation of the square deviations. And similarly, what is this? Is your bias term, correct?
Why
And
it
So
is
basically,
added?
I'll tell you that all the things. So generally,
so
what?
basically, my true mean is the population mean, right, sir?
Huh? Sorry.
True mean is the population mean, right?
True mean is a yeah, population mean. So in this case,
Population mean.
yeah, in this case, let's say w hat ml is my random variable. Okay, w is my true parameter. Fine. The bias will be what? Bias is equal to
W at my ML
no expected value of
Expected below W
w
hat
hat ml minus
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 W.
W at
this is my
W.
bias. The variance will be expected value of
W hat ML minus square.
let's say w hat ml minus expected value of w hat ml square, right? Is that correct?
Sir, expectation of
See this, you just see this one. This is what your variance is, right? Okay, I'll tell you. Maybe if you guys have forgotten, let's say if you have this random variable x, you have these values like 1, 2, 3, 4, 5. How do you find out its variance? You find out its mean first, right? Which is nothing but the expectation of x. What is the expectation of x? 3 in this case, right?
yes, 15 by 5 is 3.
So x minus expected value of x, right? And you take a square of it. So it is minus 2 square,
Minus
minus 1 square, 0, 1 square, and 2 square, right? And then you take the summation of it, correct? And then you take the average, right? Average of this. Is that correct?
10 and upon and 5.
So no.
Correct,
What
correct.
you just take the square average. Average means what? Basically, you are taking the expectation only, right?
Yes.
So finally, it's your expected value of the deviation inside that to the square, right? That is what your variance of x is, right? And in this case, what will be the variance of w hat ml? It is this
Constant.
w hat ml minus the expected value of w hat ml and its square. I will just write it properly, maybe to uh, understanding. Yes. W hat ml. It's, square of it, right? This is my variance. Fine. And what is the risk? or if you don't know what is the risk, basically risk is equal to bias square plus the variance, and that quantity is actually nothing but expected value of w hat ml minus w whole square. Okay, is that fine? If you just
सर ये रिस्क होता क्या है? ये रिस्क क्या होता है?
risk is this one, this quantity, bias square plus variance, this one plus this, that is risk. Okay, I will not go into the statistical things there. I'm just telling about basically it is the mean squared error between the parameter and the true parameter, the estimate parameter estimator and the true parameter. It is a mean squared error basically. So how much it is differing? So let us say you have this as your true w. Okay, this is my true w. This w at ml is what? It's a predictor, right? So it may have some directions, right? May have like so many directions possibly. What we need to find out, what is the average deviation from the true w, and that average deviation square, like, or mean squared error, right? Whatever the error is there between the true prediction and the w hat ml. So w hat ml, if you change the data set, right, it will change w hat ml. So in this case it was not dependent on w hat ml, is not only dependent on the data set, it is maybe it is dependent on the noise present in the data set, so it will change accordingly. Okay, I think, see, you guys have to go through the stats properly, then you will be maybe I don't know whether I'm it will take so much of time again for me to discuss.
Sir, it's okay, sir. We can have a look at all this.
We have understood the part.
Yeah, so you just basically go through that lecture once more, the stats to, I think, week 8 or 9 somewhere.
Week 9.
Yeah, you just go through that, that is important. So what we are saying, that this value, the mean squared error between w hat ml and w, which is this quantity, it is actually dependent on sigma square and the trace of this matrix
X into X transpose.
matrix inverse. Fine. So this expected value is dependent. And what is the sigma square? It's a
Is it a product?
Variance of what? Epsilon, right?
Y given X, right?
X.
Yeah, you can say that y given X, or you can say that it is the variance of a noise, right? Because
noise
is the same. Y given X also will have the same variance. So this is what it is there. And what is this X transpose inverse? This trace of this. So you will have this matrix X transpose inverse. The trace of this will be the diagonal elements, right? The diagonal elements of this. But it depends on what? It depends on the data set. So this quantity trace of this, it depends on X, right? Is it variable, or is it the constant one?
Variable.
No, X is not the variable, right? The data set is constant, right? Or okay, let us say, is it known to me or is it not known to me?
Known to us.
Right. And this, so basically the sigma square is the variance caused by the noise, right?
Noise.
So can we change the noise somehow? No, right? Noise is not in our control, correct? So noise cannot be changed, but can we do something to this data set?
Yeah, we can. Yes. The
So
features and all.
Yeah. So what this quantity actually tells me, how much far my estimator, which is done by maximum likelihood, it is from the true parameter, right? So we need this quantity higher, or we need this quantity lower. Which is better for us? Our prediction, by, like w hat ml, the estimator should be as close as
close to w.
W, right? It should be close. So that means I need this quantity to be lower, right? And this quantity is dependent on what? These two quantities, sigma square and the trace. Is that okay? But I cannot change sigma square. I cannot change sigma square. So I need to see whether I can change this or not, right? If I somehow able to reduce this quantity, trace of XX transpose inverse, I'll be able to reduce this quantity. That means which is favorable to my case, right? That means whatever the estimator I am getting by maximum likelihood, that will be the that will be very close to the exact parameters, right? Or whatever the parameter we are having, W. Fine. I hope it is clear to you.
Yes, sir.
Okay. And okay, so for any matrix, let's say A, what will be the trace of that matrix? Let's say if you have matrix A1, A2, and if you
Determinant, some of the determinant, some of the diagonal.
One, some,
sum of the diagonal,
one,
Sorry, some of
two,
the
and
diagonal.
so trace of A will be sum of A1 plus A2 plus, let's say, AN, all the diagonal elements. But is it true that the trace of A is again equal to the sum of eigenvalues of A?
yes, sum of eigenvalues is equal to trace.
Trace of the matrix, right? And product of eigenvalues will be the equal to
Determinant.
Equal
determinant of matrix, right?
product
So
of eigenvalue equal to
determinant of A matrix A, right?
yes.
So suppose XX transpose matrix, right? This matrix have the eigenvalues lambda 1, lambda 2, and let's say lambda d. If my X is d cross n, what will be the dimension of XX transpose? D cross d, right?
Yes.
So that means how many eigenvalues it will have? The maximum number of eigenvalues it can have, d.
D.
So let's say these lambda 1, lambda 2 to lambda d are the eigenvalues of XX transpose. Then what are the eigenvalues of XX transpose inverse? 1 by lambda 1,
Lambda 1 upon lambda d.
1 upon lambda d. Then what will be the trace of XX transpose inverse? 1 upon
A
lambda 1,
summation of
1 upon lambda 2 up to 1 upon lambda d. So in short, it is summation I goes from 1 to d, 1 upon
lambda d.
lambda I. Right.
Okay.
Is that correct?
Yes, yes, sir.
So then my this quantity, the mean squared error between the true parameter and the parameter which is estimated by using the maximum likelihood is actually was equal to sigma square into what this case, right? Into the trace of this. So trace is this one, summation of I equal to 1 to d 1 upon lambda is, right? So how this quantity will go lower? So we can't change this one. What should I do here? Should I add something into the numerator, or should I add something into the denominator, the any positive value? If I add
Add into the
denominator,
numerator.
let's say if I add lambda, which is,
Yes, 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 yes. Got that.
what will happen?
Beta.
The determinant become larger, and the this ratio will become smaller, right? So that means it will decrease, right? This lambda will go higher, and this entire quantity will go low, right? So if I add any positive value into the denominator, then it is possible that I'll be able to uh, reduce this thing, right? Okay. Hmm? Fine.
Sir.
Okay. So what was the W hat ML previously? It was XX transpose inverse XY. Okay. Okay. Let's say I have introduced a new estimator, which is W hat new, which is nothing but XX transpose plus lambda I inverse XY. This some I have just picked some random estimator, which is this one. Which one is better to reduce this quantity? So in this case, this quantity, the mean squared error between w hat and ml and w is equal to 1 upon lambda I plus, no, not lambda I plus lambda, it is
Yes, we have added 1 upon lambda, so
lambda I,
inverse. Yes, same
right?
thing.
And
जो
here
आपने
what
ऊपर
will
लिखा है.
happen? Yeah, sigma square into summation of I equal to 1 to d. Here also I equal to 1 to d, 1 upon lambda I plus lambda. Do you agree with this?
Yes, sir. New one is better.
So new one is better than this. So how should I add it? If I add lambda, some lambda here in the matrix, I'll be able to achieve this. Can we prove that?
How much is better? So W new को minus कर देंगे WML से.
What will be
Will you have to different?
not differentiate, not required. So
Okay.
let us say if you have A, matrix A, it will have eigenvalues as lambda 1, lambda 2 to, let's say, lambda d. Okay, A plus Ci, what are the eigenvalues of that? Lambda plus C
Lambda plus C,
and
lambda d plus C.
plus C, right? Lambda 1 plus C, and right, is that okay? So if lambda 1, lambda 2, lambda 3, they are the eigenvalues of x6 transpose. What are the eigenvalues of x6 transpose plus lambda I? Is lambda 1 plus lambda,
Lambda 1 plus lambda
2 plus
2
lambda,
plus lambda.
until lambda d plus lambda, right? And what are the eigenvalues of lambda, this entire thing, x6 transpose lambda I plus inverse, will be 1 upon lambda 1 plus lambda, 1 upon lambda 2 plus lambda, and that 1 upon lambda d plus lambda. Is that okay?
Yes, sir.
Right? So that means I should somehow uh, get this quantity, and that means I need this lambda there to have this, you know, uh, if I can be able to achieve this, then I'll be able to reduce the mean squared error between the w hat ml and the true w. Okay. uh, okay, now maybe I'll stop it here. Maybe we'll talk about the cross validation technique, which is related to this lambda, and then the Bayesian modeling in the Sunday session. Okay. I hope till now you were able to understand this part clearly.
Yes, sir.
Okay. So I'll stop it here now. I will request all of you to maybe go through the week 6 lectures before coming to the next session, so that you will be able to relate it much quickly than asking a lot of doubts, right? Okay, fine, guys. Thank you for staying so long. Okay, bye bye.
Okay.
Okay,
Thank you.
sir. Thank you so much.